Hello. Sorry I'm late. I was trying to update the website. I was trying to get the link up there for the course webs for the course. Okay. Okay, I think I've got it set up now. Can you hear me? Do you see the desktop now?
Yes.
Okay, great, thanks. Okay, I think most people are here now. Okay. Okay, we're going to pick up today where we left off on Tuesday. So I didn't put any new content up here for today. So we're going to start with the looking at the code examples in this folder on pthreads. The other day, we just talked about the idea of threads. We didn't start looking at code examples. So today what we're going to do is actually, okay, unzip this folder. Where did it go? Okay, I'm going to unzip this. And we're going to start looking at these C examples, the actual C programs, okay? And today I'm going to use this compiler. It's already on my computer, so I don't need to download it again. But I'll keep using this compiler here. If you want to follow along at home, you should be able to use that compiler to compile the examples we're going to look at today. You should be able to run them on your computer. If anything doesn't work, let me know. If you have any kind of if anything doesn't quite work right, please let me know right away. Anybody got any questions about what we talked about on Tuesday? Is there any questions about what we did the other day? Okay. Right. Let me see. Got most people are here. Oh, and yeah, I put a link up here to this was last Tuesday's talk. Okay, and then after class, I'll replace this link with a link to today's video, and if there's any new examples, I'll put them up here. Okay, but we should today just be doing the examples from this pthreads folder. And remember, our goal is to do Java threads. We're gonna do parallel programming in Java, but it's a lot easier to introduce the idea of a thread using C than it is using Java. So for the first week or so, we'll introduce the idea of a thread in C, but then we'll start really working with them using Java. Okay. Now, we drew these two pictures last time. This is the key idea for us for a thread. Every CPU executes code, and if you give me a program, there's no reason why I can't have two CPUs stepping through that same program. We think of each CPU as a thread. Okay, so that's the simplest way to think about what a thread is. You just imagine there's two CPUs executing the same program. They don't have to stay in lockstep with each other. They could be working with different data. They could start the program at different times. So there's no reason to think that these two CPUs are in lockstep with each other. So the idea is there's two CPUs executing a program. Okay. Now, if one CPU is executing one program and one CPU is executing another program, that doesn't necessarily mean you have threads. Those could just be processes. Each program is a process, and you could have one CPU executing this program and one CPU executing this program. A thread is when you have more than one CPU in a process. And we drew a more sophisticated picture of it here. The idea here was you don't really even need two CPUs. You can have threads even if you have only one CPU. What a thread really is, and this is real important, a thread is really a thread control block. The thread control block represents a thread. And what that means is, like on my computer right now, if I show you Task Manager, my program's got almost 3,500 threads, right? See, it's got almost 3,500 threads, but there's only 12 CPUs. So clearly there's not a CPU for every thread. There's one CPU for every 500 threads. Okay, so the real way this works is that you have one CPU and it's responsible for multiple threads. So here in this picture, we thought of one process having 3 threads and another process having a single thread. And one CPU is responsible for these 4 threads, okay? And it's always going to be that way because, like, I just showed you, my computer's got thousands of threads running on it, and nobody has thousands of CPUs. Nobody has thousands of cores, okay? So each core is going to be responsible for many, many threads. Okay, what that means is that core has got all these thread control blocks assigned to it. And what it does is the thread control block holds all the information about a thread. So when this thread is running, the information from this thread control block is moved into the CPU. So then the CPU is executing that thread. When it's time to move to a second CPU, to a second thread, the program counter from the CPU is put into the thread control block. So the thread control block remembers where the CPU was in that thread. The program counter from another thread control block is moved into the CPU. That starts the CPU up someplace else. That's a different thread. It might be in the same process. It might be in a different process. Like here, these thread control blocks would all be within this process. But if the scheduler decided to move from this thread control block to this thread control block, then it would be moving from this process to that process. There's not much difference. There's not a whole lot of difference from our point of view between that. The CPU can be shared between multiple threads within a process, and it can also be shared between multiple threads in different processes. Okay, so abstractly, a thread is a thread control block. Okay, the thread control block keeps track of where the thread is. It's like, a lot of people make the thread control block analogous to a little, you keep a piece of paper with you that somebody interrupts you, you can write down on the piece of paper what you were doing when you got interrupted. Then you finish doing whatever the person wanted you to do. Then when you want to go back to where you were when you were interrupted, you look at your piece of paper to tell you what you were doing. This is the thing that keeps track of what the CPU is doing when it got interrupted. The interruption is this timer. The timer says the CPU should only work for, say, 50 milliseconds on any one thread. So when the CPU is running on this thread, at some point it's going to get interrupted, just like you can get interrupted by someone. When the CPU is interrupted, it records where it was in the thread control block. You could do that by writing on a little piece of paper what you were doing when you got interrupted, so you could go back to it later on. Then the operating system tells the CPU to run some other thread. So that thread's information is loaded into the CPU. That makes the CPU start a different task. It runs that task until it gets interrupted again. And when it gets interrupted again, it might go back to that thread, in which case it uses the thread control block to remember where it was. So it's a pretty straightforward setup. It's kind of analogous to how you would imagine keeping yourself up to date on all the tasks you're doing. If you're trying to do 4 or 5 things at once and you keep getting interrupted, you might need to keep tracking a list of what you were doing when you got interrupted at each time. So that's the thread control block. Okay, all right. So that's our background. Okay, that's what we think of as a thread. We think of a thread as this thread control block idea managing a CPU. Okay, and the next level of picture would be combining these last 2 pictures.
Professor, I just got it out. So all this logic to interrupt a particular thread and to execute another thread would be managed by the operating system, right?
That's managed by the operating system, right?
Okay. Yeah.
It's specifically, it's the scheduler. It's the part of the operating system called the scheduler that manages who runs next. Is that what you mean?
Yeah.
Yeah. It's the operating system is quite large. There's a lot of parts to the operating system. The part of the operating system that decides who runs next is the thing called the scheduler. Okay, and in the operating system's textbook that I've referred you to, it's a little bit misleading here. If you read the section on scheduling, it'll say nothing about threads because the stuff about threads is later in the book. So now he didn't do it in this book, but what he really should do is, in this chapter, he should have gone back and talked about scheduling again, because here he's talking about scheduling processes. But in fact, the operating system really schedules threads. In this chapter of the book, he's thinking of one thread per process, which is kind of an old-fashioned model. So when he talks about scheduling, he's thinking of scheduling processes, and there's only one thread per process. If it's writing about operating systems is tricky because it's hard to know where to start. You can't talk about threads until you've talked about processes. But when you talk about processes, if you talk about scheduling processes, that isn't accurate because the operating system really schedules threads. But it's hard to talk about threads until you talk about processes. So you get kind of a chicken and egg thing that it's really hard to explain operating systems to people. So would have been nice if he would have had a review of scheduling in this chapter on threads, because you really have to go back and say that what the scheduler schedules isn't processes, it schedules threads. So instead of the scheduler choosing this process or this process, the scheduler chooses one of those 4 threads. Okay, so, but you can, if you want to, this chapter on scheduling is pretty well written, but it's a little bit of you have to realize that he's talking about only scheduling processes at that point. And he doesn't have anything in here where he talks about actually scheduling threads. If you're interested in more details of this stuff, you can look at more advanced operating systems textbooks, which then talk about scheduling threads. It's not that much more different than scheduling processes. You just, instead, the big difference is when he talks about CPU scheduling, what he talks about are process control blocks. So there's a process control block for each process. So he uses the phrase process control block instead of thread control block. And so the only real difference is in this chapter, he's going to talk about process control blocks, but in reality, you should be talking about thread control blocks. That's the only real difference. Okay. Now, keep clicking on the wrong thing. One thing I want to mention is that this picture represented 2 CPUs executing 2 threads in one process. This picture represents 1 CPU executing multiple threads in 2 processes. In reality, you kind of combine these 2 pictures. You'll have several CPUs, several processes. Each process will have multiple threads, and the scheduler just bounces each CPU among the different processes and the different threads. You could have more than 1 CPU executing, like you could have 2 CPUs executing 2 threads in here, while another CPU executes 1 thread in here. You could have all the CPUs executing threads in here. Oh, you would never have 2 CPUs executing the same thread. That makes no sense. Okay, you could have 2 CPUs in the same process executing 2 different threads. You would never have 2 CPUs executing the same thread. That wouldn't make sense. That would break the idea of what a thread control block represents. Okay, so you could have we should actually have a third picture that represented the idea of multiple CPUs, multiple processes, each process with multiple threads, and then the different CPUs are just bouncing around the different threads. And it's important to realize that any given process can have any number of threads it wants. If we go back over here, like right now on my computer here, yeah, you can see, yeah, some of my processes have hundreds of threads, and some of my processes have as little as 1 thread. Remember, we see the one, you're going to have at least 1 thread. Otherwise, your program doesn't exist. So a program is going to have at least 1 thread. It could have as many as hundreds of threads. Since a program could have 20 threads and I have 12 cores, it's possible that all 12 cores could temporarily be in one process. It's not very likely, but it's possible that if there was some process that the operating system decided was really important, the operating system could put all 12 cores on 12 threads in one process. Okay, but so the scheduler can do anything it wants. The scheduler can jump between threads any way it wants to. Okay, so now let's start actually executing code. Okay. Okay. Now, this is a bunch of little baby programs that try to lead up to some, they're like little thought experiments. Each one just does something really small. Okay, so none of these are complicated examples. Each one just does something small to give you an idea of build up your intuition and your thoughts about how threads work. Okay, later on we'll look at complicated examples, but we want to start with really simple examples. Okay, so here I'm going to start up this is the editor that I have tied to that GNU compiler for Windows. Here's the first example we're going to look at. Okay. Now I'm going to write some kind of, this is going to look like funny code for a minute. Okay. I have two functions down here called thread1 and thread2. They're functions that take one argument, which is a pointer to void, and they return a pointer to void. Okay. We'll see in a little while why we're using pointers to void. That's a really kind of, a pointer to void in C is analogous to a Java program that takes an object parameter. An object reference can point to any object because every object is a subclass of every object with a little o is a subclass of the class object with a big O. Okay. In the world of C, everything can be pointed at by a void pointer, which is a stupid name because pointer to void means, oh, you're not pointing at anything. The word void means empty. And here, this is just a really bad choice of words. A pointer to void means a generic pointer, something that can point at anything. Okay. So C uses pointer to voids to mean functions that can, that means this function can return a pointer to an integer or a pointer to a double or a pointer to a string. What it'll do is it'll return a pointer to void, and then you have to know what it's really pointing at. Just like in Java, when you get a reference to an object that's useless to you unless you know exactly what the object really is, then you can cast the reference to what it is. Same things we'll see here. That's what we're gonna have to do too. We're gonna have to do here too. Using this pointer to void is something that's determined by the thread library that we're going to use. We'll say a little bit more about this, but I'm using these weird pointer to voids because they're required by the thread library. Okay. But these are just functions. This is a function. Up here is the prototype of the function. In the C language, you can't use a function until it's been declared. If I want my functions down here, I have to put prototypes for them up here. If I don't want to use prototypes, then I'd have to move these functions up there because you can't call a function until it's been declared. So here I declare them with prototypes. Then I can call them here, but their actual definition is down here. So this is real standard C style programming. Okay. Java doesn't have this restriction. Java, you can write your functions in any order you want. So you can define a function after you've called it. Okay. When I say after, I don't mean after in time. I mean lower on the page. Notice that there's no time here. This is higher on the page. This is lower on the page. We call this before and this after, but there's no sense of time here. Okay. But in the C language, if you're going to call a function, before you can call the function on the page, you have to either declare it or you have to define it. Okay. Like this function here, fprintf, it's declared in this header file. So I can call this function because it's been declared in this header. That's what the header files are for. The headers gather up all these declarations of the functions that you would usually use. So like the printf function is declared in that header. If I don't include that header, I'll get a compiler error because the compiler is going to say, what the heck is printf? Okay. Warning, implicit declaration of fprintf, because now there's no declaration of it. It's been called without a declaration because I didn't include the appropriate header file. The header file just has the declaration in it. So then if I put that back, now I get the declaration. Okay. Now I get a couple warnings here because I'm not actually using these parameters yet. Okay. I have a function that takes that parameter and I'm not yet using the parameter. So I get a warning telling me, oh, you're not using that parameter. And I get another warning, oh, you're not using that parameter. That's a nice feature of the compiler. The compiler says, why did you declare this if you're not going to use it? Well, I have to declare it because of the weight of the library. We're using a certain thread library that requires me to declare that variable, but I don't have a use for it yet because the example is so simple. So for a little while, we'll get these warnings about unused variables. Okay. All right. Now, here's what I'm going to do. I've declared these two functions. I call them thread 1 and thread 2, but they're not going to be threads. I'm just going to call them as functions. Okay. So I'm going to call that function. So what does that do? The CPU is executing this program. We're going to think like a CPU. We're going to think like these pictures here. We want to think like a CPU for a little while. Okay. So when I run a C program, the CPU starts there on that line. Okay. And then the CPU steps through and it gets to that line. When it gets to that line, it calls this function and goes down to that line. Then it executes that, and that. Okay. Then when it hits the return, it returns back up to that line, which is done. So it goes to that line. That calls a function. So it goes down to that line, executes that. Okay. Then the return takes me back up to that line. Then that function's done. So then I call fprintf, and then I return. Now fprintf, the definition of fprintf is is part of the C runtime, so it's not in my code. Okay, but you call the fprintf function and you execute it, and then the program ends. Okay, so I'm sequentially, or the more fancy term is I'm synchronously calling these two functions. I call this function first and I go do what it does and I come back up here. Then I call that function and I go down through here and do what it does. The fancy term for these are synchronous function calls. Okay. Now, what does the function do? The function prints hello, then it sleeps. Okay. That's just, we'll see a little while I want to do that. It sleeps for 1 second. Then it prints out another string, sleep, then it returns. Then it calls this function, which will print out a different string, sleep for a second, then print out another string, then return. Okay. If I run this program, you can see where the sleep came from. You saw the program, print, sleep, all done. Okay, not very interesting. Okay. Now, here's what I want to do. I want to turn this into a thread function, a thread program. So go to 2A. So follow 1A with 2A. Okay, I'm going to look at these programs side by side. Okay, I think they're okay. Okay, here they're kind of lined up. There's the prototypes. There's main. Okay, now I've got a new declaration in main. I have this declaration of something called a thread ID. Okay, so I create a variable that an array of 2 thread IDs. And then here's the main difference. Let me widen this window a little bit more so the lines don't wrap. Okay. Instead of calling this function, I'm calling a function called pthread_create. It creates a thread. Okay. What that does is that creates the thread control block. Okay. Now here's what we're gonna here's what we should go back and go take this picture and go back to the first program we did. Okay. This program here has only one thread. It's like program 2. This program only has one thread, the main thread. Okay. So there's only one thread control block associated to this program. This program just has one, it only can use one CPU, and that CPU is going to call this function, step down here, return, call this function, step down here, return. So there's one CPU. Over here, this function here creates a thread control block. And essentially says, start up a second thread. So if this is the main thread here, then this line of code creates a second thread. And it says that that thread should be pointed at this function down here. So the thread control block is created with its initial program counter pointing at this function. Now, notice that that doesn't start the thread really, it just creates the thread control block. But so if you were to watch the inside of the operating system, at this point, when you got to line 24, there would be one thread control block. Then after executing line 24, there would be two thread control blocks. One thread control block would represent the fact that you're in the middle of this code, that you're at line 24, and the new thread control block would represent a thread that starts down here at line 39. Because you said that create a thread control block at that thread. Okay. Now, what's the next thing that happens? The next thing creates another thread control block. That creates a third thread control block. The third thread control block got its initial program counter pointed down here. At this point, the program's got 3 thread control blocks. At this point, if the operating system wants to, the operating system can do anything it wants with those 3 threads. So at this point, once I hit line 25, a whole bunch of things could happen. The operating system could give my program only one CPU, and that CPU could go here and keep on executing. Or the operating system could give my program a second CPU, and that second CPU could start this thread control block. Or the operating system could give my program 2 more CPUs, and one CPU would start here and one CPU would start here. Or the operating system could give me one CPU and it would move down here and do this one first. My program has 3 thread control blocks, and it's up to the operating system to decide how many cores my program actually gets and in what order. There's really no way to know what's going to happen at this point.
Yeah, so what would be the significance for the first thread created, because it's not pointing out to the any thread, right? I mean, I'm speaking about the TID2.
Say again?
When we open the program, we create we were using the thread TID2. So what would be the significance for that? Because we are not calling any thread in first TID0 and 1. We are calling thread 1 and 2, but the TID2 doesn't do anything there, right?
Okay. Whenever a program starts, the operating system creates one thread for the main function.
Okay.
I think that's what you mean. So yeah, that happens automatically for you. The first thread control block is created automatically, and it's automatically pointing at main.
Okay.
So that first thread, I see you're right. I didn't create that first thread control block. It's there automatically created by the operating system. And it was there in this program too. See, this program that didn't do any threading, it has one thread control block pointing at main, created automatically for me by the C compiler. Okay, so every program gets one thread automatically, and that thread is initially, the thread control block points at the main method. okay? So over in this one, I start off with one thread control block pointing at main. That's how I start up. Okay.
So in reality, the thread which is created would be the default thread
yes.
that creates every time, and thread TID0 and TID1 are the main threads which run the programs.
Well, there's only one main thread, thread 0.
Okay.
When your program is started, it's created with one thread, thread 0, and that thread is the main thread. Okay, so your program starts with one thread control block pointing at main.
Okay, got it.
Professor, I have a question.
Sure.
Like there are two threads over here, one except main thread. So if like operating system gets one thread execution and the second is yet to be executed, so how does this track has been kept? There is some kind of status in which the program goes, or like how it has been managed?
I'm not sure what you mean. When your program is started, it started with one thread control block, right?
Yes.
Okay, and that thread control block points at main. Okay, this function, it does what?
Creates another thread.
Thread control block. Yeah. Now at that point, it creates the thread control block. It's up to the operating system to decide whether to run that thread or not. Eventually it will run it, but it doesn't have to run it right away. So that's the scheduler. So then you're back to the idea that it's the scheduler decides once that thread control block is created, it's up to the scheduler to decide whether to actually launch it or not. You see what I mean?
Yeah. And like as soon as one thread control block is executed, so it's deleted from the system, so the scheduler doesn't do it again.
No. Yeah, the thread control block just stays there until as long as the thread is executing. This thread could run for days. Think of a web server. Think of a database server. You launch a thread, it could run for weeks. So we're not, we haven't said anything about what happens when the thread ends. Okay, so the thread, just for now, let's get used to the idea of the thread starting. The thread starts and it just runs. Okay, we'll have to say later what happens when the thread ends, but it may not end for weeks. In the meantime, this program's got multiple threads. And the CPU is going to be going from one thread to the next thread, back to one thread, back to another thread, over to one thread, over to another thread. So while these threads are running, the CPU is going to just switch between them. So that's what we're interested in, is what's happening while the threads are running. We'll talk later about how you end a thread. We'll get to it in a minute or two. But yeah, right now we want to just get the idea that this function call creates the thread. Well, it creates the thread control block. The operating system could wait. The operating system does not have to launch the thread right away. In fact, it might wait several minutes before it even launches the thread. I could call this function, and the operating system might be so busy that it might take several minutes before the thread created in that thread control block actually does anything. Oops. So the function call creates the thread control block. Then it's up to the operating system to schedule a CPU on that thread control block, which will then execute the code that thread control block represents. Okay, so I call a function that creates a thread, but then I'm at the mercy of the operating system to actually execute that thread. Now, 999 times out of 1,000, that thread will start within a few milliseconds. But on a really heavily loaded computer, it's possible that the thread might not start for several minutes. Okay. All right. Now, so back here, the program starts. It's got one thread control block that was created for us automatically. The program gets to here. It creates a second thread control block. At this point, the program has two threads. The operating system might immediately launch something into that thread there, or it might not. It's up to the operating system whether it wants to put a CPU in that thread or not. Then this gets executed. It creates a third thread control block that represents that line of code. The start point will be this function here. Okay. Again, the operating system does not have to actually launch a CPU in that thread if it doesn't want to. Okay. Now, what about this function here, though? See, after this thing has created this thread and created this thread, there's another function that says wait for a thread to end. Like, you asked about what about threads can end. The way a thread ends is the simplest way is it just returns. When this function returns over here, it's a function. Over here, it's a thread. This guy's a thread here. This guy's a function here. What does this do? What does line 30 on this page do?
It ends the function and returns the control back to the main.
Yeah, it returns it. This was called from line 16. So line 30 returns to line 16. Okay. What does this line do?
Does it return to thread 2 null?
It returns to line 17.
17.
Yeah, it returns to line 17 because this line 17 called this function. So then this thing returns to line 17. Okay, now go over here. This one's weird. That does not return to line 24. It ends the thread because over here, this was launched as a thread. So this does not return you to line 24. That doesn't make sense because line 24 just says start this guy up as a second thread. So what this is the answer to the question a minute ago. This ends the thread. Okay. Now that means that the thread control block gets deleted. It doesn't return to anything. It just ends the thread and deletes the thread control block. Okay. Similarly, this line of code ends the second thread, which would delete this thread control block. Okay. It doesn't return to line 25. Now, why is that the case? Let's think about this really clearly. CPU, let's imagine we have 3 CPUs. CPU 1, 2, and 3. CPU 1 enters main, and CPU 1 calls create thread. So CPU 1 creates thread control block, this thread control block. The operating system then launches CPU 2 in here, which is that second thread control block. So CPU 1 is up here and CPU 2 is down here. Then CPU 1 goes to this line of code. CPU 1 creates the third thread control block. But as soon as there's a third thread control block, the operating system can say, oh, I'll launch another CPU, CPU 3 down here. So now CPU 1 is over here, CPU 2 is over here, and CPU 3 is over here. It doesn't make sense for CPU 2 to return. CPU 2's got nothing to do with CPU 1. For one thing, CPU 1 did not call this function. CPU 1 called this function. CPU 1 called this function, which said construct a thread control block on this function. CPU 1 called this function, not this function. It called this function, which built the thread control block. This guy does not return to this guy because it wasn't this function call. This function call did not call that function. This function call created this thread control block. This function returns to the operating system. Actually, what it returns to is to the operating system Because once this thread control block was created, the operating system creates this thread, this new thread that executes in here. This return is analogous to this return. The main method returns to the operating system. Because this is the main thread, this returns to the operating system. Now, this is a thread. This returns to the operating system. Okay, because it was the operating system that created the thread control block. This is really complicated. And actually, once you've got your mind wrapped around this, it's not really that complicated. But it's tricky as heck to get started and get a feel for this. This function call did not call this function. This function call created a thread control block. The thread control block would then, the scheduler of the operating system called that function. That function was called by the operating system's scheduler when it saw this thread control block get created. Similarly, this function was called by the operating system when it saw this thread control block get created. That thread control block was created by that function call. Okay, but that function call didn't call this function. That function call called the creation of a thread control block. It said, build me a thread control block with that address for the program counter. That means that the thread control block represents jumping down here when it gets called. When the thread control block gets called by the scheduler, when this thread control block gets first called by the scheduler, it jumps down here. Now, when it jumps down here, it starts executing, but it only executes, remember, for 50 milliseconds at a time. You know, once the CPU jumps down here, it's only going to jump down there for 50 milliseconds. I put it sleep for 1 second. When it sleeps for 1 second, it's going to lose the CPU. The CPU is going to go do something else. Okay, so now let's run this now. Okay, so now we said what this program does. The difference. These two lines of code are replacing these two lines of code. These two lines of code call the functions. These two lines of code create two threads in those functions. Okay, then this thing waits for this thing to finish, and this one waits for this one to finish, and then this one returns to the operating system. Okay, so let me compile this.
So does this mean that this program only runs for once? Means anyways we are deleting the thread counter, right?
Say again.
Does it mean that this program only runs once? I mean, not like the other program which runs for every 50 milliseconds. This program only runs once.
I'm not sure you mean what other program? This one?
Yeah, this the left one where we are creating the threads.
No,
because
wait.
we are deleting all the threads, right?
This is the program.
Yeah.
The program, every program runs once. This program runs once too. Be very careful about how you use words. A program, by definition, runs once. This program and this program both run one time. I go over here and I say, run it one time. And then I go over here and I say, run it one time. Okay, I ran it one time. Okay, I'm not sure what you meant. So the programs always run one time. So back over here, what were you asking?
Here we are deleting the threads, right? So
no, I'm not deleting any threads.
Okay.
I'm creating threads. I create a thread here and I create a thread here.
Mm-hmm. But once when we create the threads and once the void runs, it deletes the thread. It deletes the thread when returning null.
What's it? You said it deletes the thread. What is it? Huh?
After when we are returning the null in the thread one.
When you get to the return value, the thread ends.
Oh, sorry. Yeah. Okay.
Yeah. So here, this program, okay. The operating system creates thread one for us. and runs main as thread 1. Okay, so that's the same thing as this program over here. This has one thread, thread 1, and main runs it. So this thread control block is created by the operating system, right? And that thread control block terminates when this thing returns. So when this thing returns, that thread control block is deleted, like you said, when main method returns. What does this function do?
It creates the thread 1.
It creates this thread control block here, right?
Yeah.
Then that launches a CPU over here.
Mm-hmm.
And then when this line happens, then what happens? When you get to that line, 42, what happens?
It deletes it.
Deletes, what's it?
The thread control block.
Right. Then that thread control block deletes. Okay. So that thread ceases to exist. When this line gets executed, what happens?
It deletes the thread control block, right, the third one.
Yeah, it deletes, then that third thread control block gets deleted. When there's no more thread control blocks, then this program is done.
Oh, okay. Got it.
See, when there's no more thread control blocks, that means the program is finished, and then the program ends. Okay?
Okay.
Right.
Got it.
Yeah, and this stuff is so complicated and so detailed that one of the things I try to push people to do is to talk real carefully. Because if you get in a job situation and you have to work with people, you need to really talk carefully so that everybody knows what you're asking. And because if you'll hear it when people start talking to you in real vague set things about the program does this, the program does that, it's real confusing. So you can help everybody by being really careful about using really careful terminology like, create a thread control block, delete a thread control block. When we create a thread control block, the thread control block represents executing this function. This creates the thread control block, that deletes the thread control block. Over here, this does not delete a thread control block. Over here, again, what did that do over here?
It returns to the first
right.
Line 16.
It returns it's all one function. It's all one thread. See, here there's only one thread. So that one thread goes from here down to here, then back up to here, then down to here, then back up to here. So it's all
okay, got it.
It's all one thread over here. Over here, there's 3 threads. One thread goes like this, one thread goes like that, and one thread goes like that. And no thread is returning to any other thread. So over here, one thread does that, one thread does that, and one thread does that. Over here, one thread does that, then jumps down here to that, then goes back up here and does that, then jumps down here to do that, then jumps back up here to do that. And then when it gets here, the thread ends and the program ends.
Got it.
Yeah. So notice it. Now, if you look at these two programs, if you didn't know the semantics of this language real carefully, you would think that these things do pretty much the same thing. Like all this looks exactly like all this. This looks exactly like this. The main difference is these 4 lines here versus these 2 lines here.
Yes, that's where I got confused. No, I got it. So thanks.
Yeah. Over here, these are 2 function calls. Over here, this is 2 thread creations followed by 2 thread waits. Thread join is a way of saying wait for this thread to end. Okay. Now that some people will misleadingly tell you that this returns to here. Don't think that way. Do not think that way. This does not return to here. This is just saying, I'm going to wait until this thread dies. When this thread dies, this function returns. Okay. Don't think that this thing returns to this thing. Like this one returns to there, and this one returns to there. This one does not return to any, actually it returns to the operating system. What it really returns to is the scheduler that started it. The scheduler started it, and it returns to the scheduler. But when this guy returns, the scheduler tells this guy, oh, the thing you were waiting for is done now. But that's the scheduler that does that. When this guy returns, that deletes a thread control block, and then the scheduler says to this function, okay, what you were waiting for is finished now. Okay. Similarly, when this one returns, then it returns to the scheduler, but then the scheduler informs this one that the thing it was waiting for is done. Okay. And then this thread, remember, this is all one thread. This thread can print a message and then return. Now let's watch it run. Now, okay, now look at the output. Can you see? Now look at the output. Tell me where everything came from. This HELLO came first. What line of code was that?
39.
39. Okay, but then what executed next?
The 46.
48.
Well, 48.
46.
48.
48. But then what executed next?
41.
41. What's happening there?
Okay.
Till the time it sleep, it sends the message that I think either the thread has been finished doing its work.
No. Okay. Can anybody see how to think about this? Why is this output all jumbled up? It's not got really anything to do with the sleeps. Let me comment out the sleeps. Let me see let's comment out the sleeps. Compile this. Let me run it again. Okay. Okay, now the sleeps aren't there. Okay. Where did HELLO come from?
39. Thread 1.
39. But then where did capital HELLO come from?
48.
Okay, how could line 48 follow line 39?
There are two different CPUs executing.
Yes, that's the whole
different
heart of it.
threads.
They're actually happening at the same time. One CPU is executing line 39, while at the same time, a second CPU is executing 48. And in fact, if I run this over again, I could see these things in two different orders. The capital HELLO might come out. Let me just run it a few times. Let's see if we get a different order. Oh, look, that's cute. What happened there?
It executed like 39 and 41 and 48 and
So in a
50.
sense, what's the difference between that one and this one?
Maybe once one CPU was allocated which finished thread 1, then executed thread 2.
Yeah. Like over here, all of thread 1 executed before thread 2. But here, what happened?
It was jumping between two threads.
Right, it was jumping between two threads. See, it's all random. So sometimes, now I'm trying to get thread 2 to execute before thread 1. Thread 1 started first, then thread 2 came in later. But I'm sure if I keep doing this enough time, I'll get thread 2 to come first. I've seen it before. Even though I created thread 1 before I created thread 2, I bet the operating system will run thread 2 first. There it is. Bingo. Look what happened here. What thread ran first?
Thread 2.
Oh, no.
No, small h is there.
And
Yeah,
small
there's one letter from thread 1. one letter from thread 1 came out first, and then thread 2 got its. Okay, so almost they're stepping on each other's toes, really. There's what we have now is more than one CPU are jumping in and executing the code at the same time. Okay, let me keep running this a few more times. No, it's very random. You know, what happens is completely random. Thread 1 first. Whoops. Yeah. Why do I keep getting thread 1 showing up before thread 2? Does that make sense?
Yeah, sure.
You know, why is it when I run this, I keep seeing thread 1 start before thread 2? Does that make sense? Why would I expect thread 1 to run before thread 2? Thread 1 was created first. So this thread control block existed before this thread control block. But it's entirely possible that this thread control block gets created but not run. Then this thread control block gets created and this one runs before this one. And I wish I could see that happen. I know it'll happen eventually. You know, if I kept doing this for a few days, at some point I'll get the thread 2 running before the thread 1, but I'm not getting it happening here. Okay. Okay. Now, if I put the sleeps back in there, it just makes things a little bit more. The sleeps make it impossible for all of this thread to run before all of this thread. Because what's going to happen as soon as this thread goes to sleep, the operating system is going to switch to this other thread. So by putting the sleeps in there, it makes it impossible for one thread to run entirely before the other thread does. Okay. And again, I'm going to probably always see thread 1 start first. Okay. All right. So now, okay, now a simple example like this has got us really thinking about threads and thread control blocks. Okay. So notice here's a real big thing. Is that a thread? Would you call this guy a thread?
It depends like how it's defined.
It depends on how you use it. It's defined like this. So you used the wrong word. It's not that it doesn't depend how you define it. That's its definition. In the C language, this is a function definition. Okay, so, but what you're right is it's not, it's how I use it. For example, is this a thread?
Yeah, yes, it is.
Yes,
Well,
in this case.
Yeah, here's what you should say. You should say you're using it as a thread. Okay, because let me do this. Okay, is this a thread?
Okay.
I'm asking trick questions on purpose. I'm asking subtle questions that these are interview questions. Yeah, I'm asking subtle questions here, like people would do. Is this a thread?
No.
Here's the secret answer. When everybody asks you a question in a job interview, you always give them the same answer. It doesn't matter what the question is. The one answer that's always correct is, it depends. So, is this a thread? The answer is, well, it depends. Depends on what?
How it is used.
How it is
How
used.
it is used.
Yes.
Yeah.
When I used it here, I used it as a what?
Function.
Function.
And when I used it here, I used it as a what?
Thread.
Thread. Yeah. So it depends on how it's used. You cannot say that this is a thread. It's actually a function. By definition, this is a C function. Okay, so what it is a function. It is a function. Here it's used as a function. Here it's used as a thread. Here, this one is a function. Here it's called as a function. Here it's created as a thread. Okay, so you can't look at this code and tell me exactly how it's used. You can tell me, it is a function. Okay, it's not a thread. It is a function. It's used as a function here. It's used as a thread over here. Like if I compile this program and run it. Oh, I misspelled these. I forget that this is C, not Java. Okay, there's this function calls. Now there's the threads. That output was a function call. That output was a function call. And this output was two threads mixed together. Okay, so function call, two threads jumbled up. Okay, function call, two threads jumbled up. Then I waited for them to end, and then that program was done. Okay, all right. So we're really starting to think using threads. We're starting to really think about threads and how this function can be used to either call a function or create a thread. And this function can be used to either call a function or create a thread. So this guy just is a function, but it can be used as, what we say is, the function can be used as the entry point for a thread. When I call create thread, I'm saying use this function as its entry point for the thread. So the thread starts there. And this thing says, use this function as the entry point for a thread. So the thread starts there. Okay. All right. So, 20 lines of code, you can spend an hour talking about it. This is how you know you're in more advanced programming classes. Okay. You write 20 lines of code and you spend an hour explaining what it does. Okay. All right. Now so let me close this. So we've looked at, now this was 1A and 2A. Let's look at 1B and 2B. They're just they're more or less the same thing, but in just a slightly different style. Okay. Okay. So I'm going to open 1B this time. Okay. 1B, very much the same thing. There's the prototype for the two thread functions. I'm going to call them as functions. And here what they do is, instead of sleeping, each function just prints out a letter for 1,000 times. Okay, so print the letter A 1,000 times. That's what one function does. And the other function prints the letter B for 1,000 times. The other example used the sleep to take time. This uses printfs to take time. So if you run this, it takes a while. See, it takes about half a second to print out the A's and about half a second to print out the B's. Okay, so all the A's got printed, then all the B's got printed. Okay, now I want to switch to, I don't want to call that as a function. I want this guy as the entry point for a thread, and I want this guy as the entry point for another thread. So that's 2B. Oops, I opened the wrong file. Okay, so, okay. There's the function version. There's the thread version on the left. Okay, all right. Now, again, it's the same thing we just talked about. Create a thread control block with that as the entry point. So that makes this the entry point for a thread. Create a thread control block with that as the entry point. So that creates this other thread, this other function as an entry point for a thread. Run them, well, compile it. Now run it. Okay, what did I see?
Random, I mean, it's jumping between the threads. Again.
Yeah. The scheduler is jumping between the threads. So one thread is running, so it's printing its A's, then the other thread is running, so it's printing its B's, and you see a random jumble of A's and B's because the scheduler is jumping between the two threads because they only run for 50 milliseconds at a time. So each thread gets a little bit of time to run and it can print out a few A's. Then the other thread runs, it gets out a few B's. Then the other thread runs, it gets out a few A's. So you actually see the jumping back and forth between the threads. That's what I like about this version of the example. You can see the jumping back and forth. If you run it, and every time you run it, it'll be a little bit different. It's never going to be the same. Every time you run it, it's going to be different. Now notice I always start with A's. Okay, why do I always start with A's?
First thread.
Because the one thread control block is created before the other thread control block. So the operating system probably starts that thread before this thread control block even exists. More than likely, as soon as that function is called, that thread control block gets created and the thread gets started right away. Now, there is a small chance that this thread control block can get created, but not started. Then this thread control block can get created and it can get started before that one. And I mean, I've seen it happen. It doesn't happen very often, but every once in a while, if you keep running these, if you have the patience to keep running these, you will probably eventually see one where thread B, the second thread, starts before, it happened. Yay. I got one. See, the second thread started first before the first thread. So that means now I got this kind of a bit of an odd situation where this thread control block was created, but nothing was done with it. This thread control block was created. That thread got launched. And then after that thread got launched, the operating system went back and launched this thread. So the thread that got created first got ran second. So you see the B's coming out first, then you see the A's, then B's, more A's. Okay, right? So, but you can see how the two threads are running in parallel at the same time. Okay. All right, now let's look at some more examples.
I just have one doubt. Is there any way that someone can predict which thread would be called first?
No.
Okay.
It's up to the operating system. It's entirely up to the operating system. One of the things you're taught in this stuff is never think you know what the operating system and the scheduler is going to do. You do not know what it's going to do. Okay.
Yeah.
Now, there are some subtle things you could do. For example, you can create a thread with a higher priority than another thread. The thread with the higher priority will start first, but that's a more advanced topic. So then you're starting to play games with priorities and things like that. So you could guarantee that one thread runs before another thread, but you'd have to do it by creating the thread with a higher priority. But that may not be what you want. That may not be what you really want either. Okay. So for the most part, the rule is you never know what order these threads are going to be run in. You can create the thread, and then it's up to the operating system to run them. We say that it's indeterminate. You do not know what order this stuff's going to happen in. Okay, let's look at 3. Oh, the A versions all run as functions, and the B versions run as threads. So every one of these, the A and the B versions, they differ by the A version being, no, I'm sorry, that's not what I meant. The A version uses the sleep, and the B version uses the string of A's and the string of B's, okay? So the versions that are called A use sleeps to separate the behavior of the two threads. And the ones that call B, they use a long string of A's or a long string of B's to see the difference between the two threads. So let's look at 3A. Okay. 3A is going to be kind of quirky. I've got two functions down here. Okay. Now here's what's going to happen. This is only going to create two threads. So when the function starts up, I have a thread control block that is the main thread. Okay. Then I create a second thread control block. So now I have two threads. Then the main thread calls this function here. So this function here is called as a function, but the thread calls, so this is used as a thread and this is used as a function. So the main thread creates a second thread, then calls this function, then the main thread comes back up here and waits on the other thread. This is a real common pattern. In the previous example, I really didn't need 3 threads because I was only doing 2 things at a time. So since I'm only doing 2 things at a time, this guy and this guy, I don't need 3 threads. So what I'm going to do is I'm going to use the main thread to do this work while I use a new thread to do this work. Okay, so the flow here is the first thread comes in here, the thread that the operating system gives me, the main thread. The main thread comes in here. The main thread asks for a second thread to be created using this function. Then the main thread calls this function. Then when this function returns to here, the main thread waits for the other thread to finish, and then the main thread knows that everything is done. Okay? Now, if you run this, it runs exactly like the other versions. Okay, you've got 2 threads running these 2 functions. In the previous version, the main thread did nothing while the 2 threads ran these 2 functions. Now there's only 2 threads. The main thread runs one of these functions, and the second thread runs the other function. So the behavior is exactly like what we saw a minute ago. Okay, so it's written in a different style, but it behaves exactly like what we saw earlier. Okay. And if I do it with here's the version that uses the strings of A's and B's. This thread prints out this function prints out 1,000 A's, and this function prints out 1,000 B's. The main thread comes in here. The main thread asks for a second thread to be executed in this function. So the main thread asks for a thread to execute the A's. Then the main thread goes down here and the main thread prints out the B's. Now, notice, which do you think I'm going to see first now, A's or B's?
B's.
Why?
The main function just created a thread and it continues with the execution of the function.
Right. So the B's are coming from the main thread, which is already existing. The A's come from the thread that needs to be created. So more than likely, the B's will come out first than the A's now. Okay. Now the B's coming out first is more likely. Now, it could be that the scheduler could, when it creates this thread, it could stop the main thread, start up this thread, print out A's, then go back to this thread and let it finish. So let's run it. Let's see what happens when we run it. We'll probably, okay, compile it. We'll probably see B's before A's, but it's not guaranteed. Okay, B's before A's, B's before A's, B's before A's. Now, if I run this enough times, I probably will eventually get an A before the B's. What that would mean is that the operating system created this thread. And then before it actually went back to here, the new thread got launched, printing A's before you even came back to this function call here. Okay, let's see if we get one of those. It's probably going to be kind of hard to get one, because the main thread is just running already. So the main thread, more than likely, the thing that's more than likely is this function call creates a thread, returns, you immediately launch this function here, and then while this function's running, this thread gets created. It's probably going to be pretty hard for me to get A's before B's in this case. Wow, look at that, almost. I got one letter B before the A's came out. So that means that this other thread got launched almost exactly at the same time that this function got called. Okay, so I almost got the A before the B's. So if I keep trying, yeah, I might be able to get an A before a B. Okay, you notice that every time you run, it's different. Okay, all right. Okay, so now notice one of these is being used as a thread and one of them is being used as a function. You can't look at this guy and tell me what it is. Well, you can. This guy is a function. Okay, this is a function. According to the C programming language, by definition, this is a function. But a function can be used as the entry point of a thread. So here I used that function as the entry point of a thread. Okay, and I can do both. I mean, I could, if I wanted to, I could do the following. That's going to use this function as both a thread and a function. It'll create a thread in this function, then it's going to call this function. That means I'll get 2,000 letter A's and 1,000 letter B's. There'll be 1,000 A's from this function, from this thread, 1,000 A's from this function call, and 1,000 B's from that function call. Okay. Notice I got the A's first, because now those A's came from this function call. Okay. Then this thread would kick in some more A's, and this thread would put out the B's. Somewhere in here are, notice I can't tell which A, I can't tell which A's are from this thread and which A's are from this function call. There's no way for me to tell which ones are which. So there's 2,000 A's and 1,000 B. The first A's come from the function call. Well, we don't even know. The first A's could come from the thread. The thread, we really don't even know which, that A there, we have no way of knowing if it came from this thread or that function call. Probably came from this function call, but we don't know that. Okay, so I can use that function any way I want. I can use it as a function, or I could use it as a thread. I could use it as a function. I could use it as a thread. Okay. Okay, let's look at another example. Got a couple more minutes. Oh, do we have more? Are we done? I forgot to check time. Actually, we're done, right?
Yes.
Yeah, we're supposed to end a few minutes ago. Okay, so we'll quit here. I don't want to hold you. I don't want to keep you from dinner. Okay, so what we'll do then is next week we'll just look at some more examples here. Yeah, there's just more examples here of this distinction between a thread and a function, and just looking at some of the differences of what we mean by code as a thread versus code as a function. Okay, so okay, so we'll stop there, and let's see. We don't meet. Oh yeah, we meet on Tuesday. Monday's a holiday. but we have class on Tuesday. So we'll do some more examples of these on Tuesday. Anybody got any last minute question? Any last minute question?
A question, but not exactly related to it. Is it fine?
Sure.
Like, do a scheduler maintain some data structures for CPU to tell them
Say again.
the next set of do scheduler have some kind of data structures for the CPUs so that they know which needs to be executed in the next section, right?
I'm not sure what you mean. How does it choose between which thread to execute?
Yeah, it's like scheduler performs, like scheduler knows, like first it will execute like for program 1 TCB1, program 2 TCB3. So do these instructions are stored in somewhere for the CPUs to like follow those?
Well, yeah, they're part of the operating.
Just happening at the same time.
Are the threads executing at the same time? I'm not sure.
Okay, maybe next time I'll have a proper understanding.
I'm not sure what you're asking. I mean, the scheduler is the one who chooses what thread to run. And every operating system has a different kind of scheduler. And the schedulers are very complicated pieces of code, but the job of the scheduler is to pick a thread to run next. And there are multiple data structures and algorithms involved in the scheduler. But yeah, that's kind of like a generic answer is.
Okay. Yeah.
Okay. Hey, anybody have any other question?
I just got a question regarding the subject, but for the course. So this course is all depend on the assignments you give, right?
Yes.
Oh, yeah, that's what.
Yeah, and I hope to have one out pretty soon.
Yeah, thanks for that. Yeah.
Okay.
Just wanted to.
Okay, so I'll stop. I'll end the class here. Have a nice weekend. Bye-bye.
Bye, sir. Have a nice weekend.
Bye.